Hello wonderful viewer and welcome to What the Math. This is Anton and today we're going to be answering a few questions that have been raised about black holes in some of the previous videos that you can find right here. Now I also would like to thank all of you for helping me reach the 15,000 subscriber mark. We have made it and it's all thanks to you guys. Thank you for all your support, thank you for all awesome comments and questions and for being awesome subscribers. Anyway, so let's actually talk a little bit more about black holes because I realized that making those videos raised a lot more questions than answered questions. So today I'm going to try to clarify some of the things. Welcome to What the Math. And first and foremost, I would like to thank Michael Miller and I hope I pronounced his name correctly, Arthur Renato Bibi. I hope that's the name that you have. Anyways, thank you so much for telling me about the version 0.974 beta. I didn't know there was a beta version that was actually stable enough for me to use in the videos because Space Engine is actually I'm going to talk more about this later, but they've reached a new fundraising mark where it's actually going to be released on Macs very soon and also possibly other platforms as well. And there's a lot of new additions that are absolutely amazing. So why am I looking at this star? That's because it is not a star. This is one of the additions to the new version of Space Engine that's going to be coming out really soon. That's right, look at that. This is a black hole that has an amazing accretion disk orbiting around it. Now, this is actually 1 second per second, so I have to slow down time just to show you what it really looks like. So it's a very, very fastly spinning black hole that has a huge accretion disk around it. This black hole is not particularly massive, so actually if I were that close to it, I would already have been killed miserably through spaghettification, about which I talked about in the previous video. But here, you are actually now able to approach the black hole and sort of see this really cool effect, very similar to what we see in the Interstellar, that sort of had a very similar supermassive black hole that had an accretion disk. We'll talk more about accretion disks a little bit later in one of the future videos because today we're just going to answer a few questions and clarify a few of the confusing things that have been raised in my previous video. So first of all, let's actually move away from this black hole for a second. We're going to come back to it in a second because I have it saved, and we're going to go to the previous black hole that I explored when just looking around new galaxies that have been created in this beta version of Space Engine. So this black hole right here is actually part of the binary system and is not a very massive black hole. It doesn't actually have an accretion disk. It's just an empty black hole all by itself. It's actually kind of hard to find as well, so I do need to use this right here to try to point out where it is. All right, there it is. So let's move closer to it. We're going to go to Object, and I'm going to show you one of the really cool additions that have been added. And you may have already noticed it, so let's just remove the orbits for a second, just so you can see it better. What has been added, and this is actually something that I'm going to be exploring in more detail in the next video as well, but basically we now have blue shift in the game. As I'm approaching the black hole, the space-time warps around me, or basically the entire space-time around the black hole starts warping more and more, and the light behind the black hole starts being blue shifted, and you can see it's becoming more and more blue because it's being sort of, I guess you could say, launched at me, or that's not really the right term, but it moves toward me with a lot more energy than before, and because of that, it's being blue shifted and everything around me becomes very, very blue. Now, first, what I wanted to really show you in this particular simulation is what really happens visually when you enter a black hole. And this is, I'm really happy they finally added this to the game because it wasn't really possible before. But so what happens when you enter black hole? Like I mentioned before, first of all, obviously the time around you will start speeding up, so everything will be moving a lot faster. You'll start noticing stars whizzing by. The entire galaxy will start spinning faster and faster. Also, you'll obviously start seeing a lot more blue shift. Things will even become more ultraviolet, more X-ray-y, and a lot of these waves will eventually become invisible because they'll become ultraviolet. So right before I enter the event horizon, if I look around here, a lot of things are very, very, very blue because they're very blue shifted. Now, and behind me, that's what it looks like as well. Now, as I move closer and closer to event horizon, I'm going to look into my side window now. This is what's going to happen. At some point, half of my view is going to be event horizon, the blackness, and half of it is going to be this blue shifted universe that is moving really fast around me. It's sort of fast forward. Oh, there it is. You could actually see the star whizzing by. It's fast forwarded because I am now in such a tremendously warped space that everything around me is not experiencing as much time dilation as I am right now. And so I am essentially now a time traveler, which is actually a pretty cool concept when you think about it. And I think this brings me to one of my first questions here. And the first question is from Rage Bogey, I think. And the question is, why does time speed up? And also, how come I don't actually feel it? Well, so why it speeds up is a very interesting question. And that also relates to the idea of space-time. So I'm going to kind of tease you a little bit and exit the black hole for a second. I'll show you what the inside looks like later. And so why does time speed up? Well, because everything here, everything in the universe, everything around you, everything around us is essentially space-time. It's not space, it's not time, it's space-time. It's sort of like the same two faces of, different two faces of the same coin. So think of a coin that has two different faces, so that's space-time. Actually, this idea is not from Einstein, it's from his mathematics professor by the name of Hermann Minkowski, who originally, something like in really early 1900s or possibly late 1800s, came up with this four-dimensional idea of space-time. And so you really have to think about space-time as a kind of a continuous one thing. It's not two different things. Time is not separate from space, and space is not separate from time. They're basically just one long, voluminous, huge thing. A thing that can actually be manipulated, it can be stretched, it can be condensed. And because it can be stretched and condensed, obviously one thing will influence the other. And so when you're actually next to a very massive object, which obviously warps space around it, the time will also be influenced. And so here you have to really think about perspective. So even though from one perspective, time may actually seem like it's moving at this fast pace, if you were to go into a different perspective, time would now, because there's no more mass influence in it, time would now move a lot slower. Where's that star? I don't even know where it is anymore. It flew away from me. But there it is. So time in a different perspective, even though you look in the same object, now actually moves differently because you're really looking at all of this from a completely different view now with a completely different space-time parameters. And so this is kind of similar to the idea of just looking at objects in space. So if you were to look at a star, if this star is, let's just say, how far away is this? It says 15 light years away. What I see from my perspective right now is actually an object that emitted light 15.5 light years ago, and I'm actually seeing the light that is 15.6 years old. I don't see the real light that this particular star emitted. So this light is already 15-something years out of date, and we can therefore never really know what the universe is like at any instant. Because universe doesn't just exist in space, it actually exists in space-time. So both space and time are related. For me to see what the star is really like, I have to approach it, and as I approach it, time will pass. And so obviously to cover this space, I will have to spend time. So once again, space-time is related, and what I'm seeing from my perspective is very different from the perspective of that particular star. And so in today's modern science and in physics, we don't really think of time as passing or flowing. Time doesn't really behave in such a manner. As a matter of fact, the way we think about time is that it's essentially just there. The past, the future, and the present are basically laid out already in this so-called space-time. It's already there, and essentially it can be explored in both directions. Now, if this is all confusing, you are not alone. Don't worry that if you didn't really understand what any of this means, but think of really this whole space-time thing as mass and energy. Today we know that mass can create energy. When you explode something, when you explode a nuclear bomb, you create energy, and energy can actually create mass. Energy, if you create a lot of energy, it will eventually turn into mass. And because of this energy-mass connection, you can kind of think of space-time connection as well. I think it's a pretty good analogy. So think about it. If mass can become energy and they're basically just one thing, why can't space and time be the same one thing? Anyway, moving on. Let's go to the next question. And the next question is from a person by the name of Ahmed Sao. And now, this person actually asked two questions, but I want to answer the second one because I'm going to answer the spaghettification question in the future. But this question here, how can we see the future near a supermassive black hole? So this is how. As you approach the supermassive black hole, if you actually are right here, it's not that just that you see the future, it's that you actually see the entire universe fast forwarding, and as you pass into the black hole, I'm stuck inside of it now. As you pass inside the black hole, you're essentially are seeing the end of the universe. You're seeing the future and the end. It's not that it's the future, it's just the present for you has been accelerated into infinity. So what you're really seeing is the time outside, your time is essentially being fast-forwarded into infinity. So for people outside of this perspective, for these people, it may seem like the future, but for you, it's not the future at all. It's actually your present. It's being accelerated and moves really, 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 really fast. And a very similar question is from a person by the name of Louis Bloch, and he asked that if you go closer to the black hole and time gets faster, doesn't that mean that you just time traveled? Well, it kind of does mean that you time traveled, especially if you can actually approach the event horizon and somehow then move away from it. You will actually find yourself in the future. I mean, it will be your future. Everyone that you know has already technically died, and Earth is very likely have been destroyed as well. So it is future, but at the same time, it is once again your present, because it's always all about your perspective. And another really interesting question was from a person named Hi Bye, or is it Hi Bye? Anyway, he actually asked quite a few questions, or possibly she, and one of the questions was this. So, is it true that the gravity also slows down time, not just speed? And the answer is yes, it's true, and this is why the time would slow down if you come close to the black hole. But what I wanted to talk about is not actually a black hole, but the real phenomenon that exists on Earth, and that is very, very important for us when we're using things like GPS. And for this particular simulation, I'm actually going to try to come closer to this planet so you can kind of visualize what's going on here. We're going to slow down time a little bit because it's spinning a little bit too fast. I believe this is some sort of a cool ice giant. So on our planet, if you stand on the surface of our planet, and I don't know if I can land the surface here. Yeah, look at that, we can. If I am on the surface of this gas giant, the time for me is actually moving a little bit slower than the time for an astronaut or for a satellite that is above me. Because I'm closer to the gravity pool of our planet Earth, and or in this case, this particular cool ice giant, that's actually what it's called, cool ice giant, the time for me, because I'm closer to the pool, here is actually slower than it would be here if I was in orbit around it. And for this particular reason, our GPS satellites have to actually actively calculate the gravitational effects and the time dilation effects, and have to actually add something like a few milliseconds every year or so, because since they're actually above us, they don't experience as much time dilation. And for this reason, let's just actually imagine this for a second. So let's imagine you have a twin brother or twin sister, and you decide to stay on this ice giant inside this really cool looking hurricane. So you're basically closer to the surface of the planet, and your brother or sister is somewhere outside orbiting around this planet on some sort of a new space station. After a few years, your brother or sister comes back to the planet, and you'll realize that he or she is actually a few milliseconds older than you, because they've experienced time dilation a little bit different from you. So this is kind of how it works, and this is why our GPS systems have to be always constantly adjusted for this type of a dilation, otherwise they will not be very accurate. Alright, so let's go back to that black hole, and I'm going to answer one more question that's actually, I guess many of you have been asking and kind of wanted to know what the answer to that is, so we're going to go back here. And the question is this comes from a person by the name of Advanced Prime. What is the theory, or what is my theory of what happens when you enter the black hole? Now, so this is actually what I really wanted to show you in this video. This is the new addition to this simulation. And this is the visual representation of what happens when you enter a black hole. And then I'm going to talk about the theory of what might happen afterwards. We're going to be entering this event horizon. We're going to be looking into our side windows, because in front of us is just blackness. As you pass by the event horizon, at some point, if you were to look back, this is what you would see. The entire universe, everything in the universe would start slowly be turned into this, a tiny circle. This is not just what you see behind you, this is everything. Everything would become a circle, it would accelerate in time and would accelerate into infinity and then disappear forever. Forever and ever. You would see nothing afterwards. That's it. You're in complete darkness. You're inside the event horizon. You're inside the black hole. Now, remember how I told you in the previous video that every other event would also be actually seen in this particular moment, and this is what I think would happen. So because every other event that has crossed event horizon would now be in front of you, or possibly behind you, but very likely to be in front of you, because there's really only one direction now. There's only this center, which is towards Singularity. You would now be able to essentially see, and I guess maybe even feel, everything at the same time. All of these events that crossed the event horizon at some point would now be right in front of you. Now, this might not last very long, and depending on the size of the black hole, it might actually last only a few seconds, because as you approach the Singularity, theoretically what should happen is that you should finally be spaghettified, you should finally reach your destruction and be completely destroyed. But it's very likely that you might also end up in a completely different universe, in a completely different place. And this is actually what I think would happen, because you're now in a completely new environment where you have, not just environment, completely new universe that has all of these events that crossed with you that are actually not present in the previous universe anymore. So that universe that we've left, it's gone forever. You cannot return to it anymore. You're now in a new universe and have all of these events that crossed into this universe with you. And so now you might actually have a completely new life in a completely new universe. And that's, I guess, more of a positive thinking. But anyway, we can actually, at least in this game, fly through this black hole, and we can actually possibly even come out on the other side. I missed the other side. There you go. We are now going to be coming out on a completely different side of this black hole. And this is what you experience if you were to kind of be able to come out of the black hole. But this is not even theoretically possible. It's impossible to come out of the black hole or the event horizon, at least without some sort of a theoretical concept that we haven't really come up with yet. So technically, once you go in, that's it. And what happens afterwards is anyone's guess. Anyway, so before I finish this video, I actually just wanted to answer one more question, because it's kind of, I think it was a pretty good question. It's actually one of the more unusual questions that made me think. And the question is this, and this is from a person by the name of Kawaii Ninja. What happens if the solar system is near all the star clusters that's around the black hole? Will the sky be very bright? And that's an excellent question, because it absolutely is true. It will become very, very bright. I'm going to show you using the new addition to the game, which is obviously the actual central black hole in our galaxy. If I were to go to the supermassive black hole in the center of our galaxy, this is what it will look like. And let's just say you're orbiting somewhere here, or basically this is your home star. This is where your home planet is. If you were to look into the sky from this home planet, the sky would be ridiculously bright, much, much brighter than our sky, because the center of the the center of the galaxy, near the central black hole, has so many more stars than the part of the galaxy where we are. And because you're so close to the black hole, there's actually a lot more stars orbiting around it, so you would actually see something like this. And this is obviously accelerated, but you would see a lot of these stars just kind of orbiting around you faster than usual. As a matter of fact, every year or so, your actual view of the sky would change completely. So keeping track of constellations and keeping track of actual stars would be relatively challenging, because there would be just a lot of motion, a lot of really awesome bright skies and bright lights everywhere. And obviously, you would also have this really, really interesting, really scary looking black hole in the sky as well. And you would really only see the accretion disk and possibly any kind of effects from collisions with the black hole, because whenever a collision with the black hole occurs, it does release a lot of energy. But depending on how far away your actual home planet is from this black hole, you may just see a kind of a bright light right there. So it's very difficult to see it. We're gonna have to come closer just so you can see it. But the accretion disk here is essentially what creates this type of a look. So it does kind of look like a star, but it's not really a star. It's really a supermassive black hole with a lot of energy and a lot of accretion disk particles orbiting around it. And anyway, let's go back to Sagittarius A. This is our central supermassive black hole. It's finally been edited to actually represent what it really looks like, and it has its actual realistic mass of 4.3 million masses of sun. And this is the stars orbiting around it as well. These are the stars I talked about in one of the previous videos. Anyway, hopefully I kind of helped explain some of these questions you guys had, and hopefully I made this a little bit more clear. If I made this more confusing, please post more questions so I can answer them as well. And I guess the takeaway message from this entire series on black holes, and also this video in particular, is that you have to just remember that, let's actually slow down time before I explain this. You have to remember that there is something called cosmological principle, and this principle refers to a simple idea. The center of the universe is actually everywhere. Scientifically, you are the center of the universe, but then again, so am I. So is this black hole. So it's really all about the point and the perspective from which you're observing the universe. So if I'm observing the universe from the perspective of very close to the black hole, my entire universe is different from yours. And my time, my space, and everything in time-space for me flows very differently from you, where you are. And this is the really important concept in physics and in astrophysics as well, because this is essentially how the entire universe works. And so whenever you're trying to think about the universe, think about any kind of stars or any kind of black holes out there, you really have to always think about the perspective from which you're actually thinking about them. And so this cosmological principle is the reason why universe is actually so counterintuitive and so complicated. Anyway, I hope you enjoyed this video, and I hope I answered some of your questions that you had in previous black hole videos. And thank you so much again for helping me reach 15,000 subscribers. I love you guys so much. Thank you for everything. Feel free to post more questions. They'll definitely be answered. And if you want to contact me, don't forget there's always the Facebook page that I usually check very often and always answer every question there as well. Also, don't forget that the Space Engine is actually free, and the new update that will include Max is coming out really soon, so do check it out and make sure to download it if you still haven't. Finally, check out the Patreon page that I started a few months ago. If you don't mind supporting me a little bit more, that would be actually very helpful, because I'm actually trying to buy a better camera right now, so I can try to put more face cam videos that actually look better than what I currently have with my really bad laptop webcam. And finally, if you still haven't subscribed, don't forget to subscribe and share this video with people that you think may want to learn more about black holes and enjoy videos about space, science, math, and all that stuff. Anyway, thank you so much for watching, guys and girls. I really appreciate all of your help. Game you later. I'll see you in the next video. And as always, bye-bye.